Hi, my name is Jihan Lee. I am a first-year graduate student at the University of Texas at Austin. I'm going to present my research paper on dark matter deficient galaxies and their member star clusters that form simultaneously during high-velocity galaxy collisions in 1.25 parsec resolution simulations. I conducted this research with Eunjin Shin and Jihoon Kim and at Seoul National University. For more information, please refer to the journal or archive number at the bottom. So first, I will start with the lambda-CDM cosmology. In lambda-CDM cosmology, structure formation occurs in a bottom-up manner, starting from primordial density fluctuation, which imprints its trace in cosmic microwave background, as shown in the left plot. Dark matter gravitationally collapses to form dark matter halos. As you can see in the movie on the right side, small dark matter halos form firstly and merge with each other, producing more massive halos. Since baryons have high temperature, they need more time to cool. Dark matter firstly builds the skeleton of baryonic structures like galaxies and galaxy clusters. As you can see in the left figure, the stars live within filamentary structures of dark matter skeleton. Then gas fall into sufficiently massive dark matter halo and form stars and galaxies. You can see in this movie. So most galaxies that we observe today contain a great amount of dark matter. However, Bandacom about 2018 and 2019 found that NGC 1052 DF2 and NGC 1052 DF4 ultra diffuse galaxies with stellar mass of 2 times 10 to the 8 solar mass located nearby giant elliptical galaxy NGC 1052 have only little dark matter. So the mysterious small fraction of dark matter in those galaxies cannot be explained by the conventional galaxy formation theory in the lambda-CDM cosmology. Also, observations performed by several observation groups show that DF2 has another interesting characteristics. DF2 has unconventionally bright population of globular clusters. GC population has a peak at -9 magnitude, which is 1.5 magnitude brighter than mean luminosity of typical Milky Way GCs. Their size and ellipticities are also very large compared to Milky Way GCs. You can see it in the figures from Bandacom group and other observation group. Although there are quite large uncertainties in observations presented here, I will briefly summarize the observation results. The age of DF2 is about 8 to 10 giga-year, and the metallicity is about -1 to -1.2. And Fench et al. Observed small difference between metallicity of GCs and the stellar body. So the discrepancy of metallicity may suggest that stars in GCs and outside of GCs, which is stellar body, may have different formation history. To address these enigmatic properties of DF2 and DF4, Lots of researchers suggested various formation scenarios. In our research, we demonstrate the scenario suggested by Joseph Silk. He suggested that high-velocity collision of two gas-rich dwarf galaxies, an event that is comparable to the famous bullet cluster, is shown here, can produce DMDGs. Because dark matter is thought to be collisionless or has very small cross-section, even in the case of self-interesting dark matter, when two galaxies collide head-on with sufficiently high velocity, maybe about a few hundred kilometers per second, dark matter will just pass through. However, gas which is collisional experiences ram pressure, produces strong shock, and loses its bulk velocity. Therefore, as you can see in the observed image of bullet cluster and central figure on the right, gas can be separated from dark matter. So we try to demonstrate the scenario by using simulation codes. Here are the structure parameters of dwarf galaxies used for the initial condition of the simulation. Two gas-rich dwarf galaxies of total mass about 5.5 times 10 to the 9 solar mass collide with relative velocity of 300 kilometers per second. In the bottom table, runs with different stellar feedback inertia and initial metallicity are summarized. So we'll mainly talk about fiduciary run. In our previous study, Shin et al. 2020, which I also co-authored, we demonstrated that DMDGs can be produced during high-velocity collision of gas-rich dwarf galaxies. So the simulation was carried out with ENSO code, and its resolution is 80 parsec. At the end of the simulation, in the dashed circles, like this, we can see that there are only stars but no dark matter. We found that collision dramatically boosts the star formation rate when two galaxies approaches, which is marked as red dashed line. It peaks about 1.4 solar mass per year. The most massive DMDG has star mass about 1.6 times 10 to the 8 solar mass, which is similar to the observed value of DF2. So you can see in the right plot the profiles of enclosed mass of the most massive DMDG. So far, by using 80 parsec resolution from our previous research, Shin et al. 2020, we successfully presented the formation of galaxies without dark matter. However, spatial resolution of 80 parsec and mesh resolution of 40,000 solar mass are not enough for preserving star formation of individual gas clouds. Therefore, we tried to increase numerical resolution in this work, Lee et al. 2021, by significantly improving resolution and could reach 1.25 parsec resolution that can resolve star formation in star cluster scale. So here are the summary of simulation details. And so new initial condition was created with larger number of dark matter and star particles. And you can see that we increased level of adaptive mesh refinement, AMR, and could achieve 64 times better resolution. And however, we applied AMR only for the region of interest to reduce computational load. And also we changes star formation threshold density in stellar feedback physics to resolve star formation well. And also star particle mass has changed a lot, which means we resolve star cluster better. Here is the movie of the whole simulation in this work. So you can see that dark matter passes through here and gas remains near the collision point, and then they form dark matter galaxy as shown in the dashed circle. The most massive DMDG in this simulation has stellar mass of about 3.47 times 10 to the 8 solar mass, and also without any dark matter.
800 after the pericentric approach, 42 gravitationally bound star clusters orbit DMDG. So here, star cluster 1, SE1 to 5 are the 5 most massive star clusters in our simulation. So the middle panel here shows dynamical mass estimated from each star cluster's velocity and position, agrees well with enclosed mass profile, which is indicated with dotted line. So we can say that star clusters are being visualized, which is a key assumption of dynamical mass estimation using Virial theorem. So here we present a movie that shows the formation of star clusters and its orbit motion. So you can see the star cluster particles, red particles, are formed in dense gas clump at the beginning of the movie, and it orbits DMDG here, which is indicated with gray particles. So the surface density in the dense clumps where the star clusters born is more than 10,000 solar mass per square parsec. So this leads to efficient star formation and massive star cluster formation. And this figure shows that DMDG stars, black lines, and star clusters, colored lines, are formed simultaneously within 150 mega year. So we can say that massive star clusters and DMDG formed simultaneously during high velocity collision. Here is an analysis of star cluster properties in comparison with the observed values. So stellar mass of star clusters is between 10 to the 8 and a little more than 10 to the 6 solar mass. Metallicities and creation time of star clusters and DMDG stars differ slightly, as you can see here, and star cluster. And half line radius or half mass radius estimated absolute magnitude of star clusters are shown in this plot, and they are in line with the observed result from Van de Kum et al. And Ma et al. Also, juicy population, star cluster population is slightly brighter than nuclei GCs, and massive star clusters overlap with the observation. Now I'm going to present parameter study of DMDG formation. We performed several simulation runs with different stellar feedback energy and initial metallicity. In this movie, in this movie you can see that a series of runs with different stellar thermal feedback energy creates, indeed, DMDGs and star clusters, but in the run with stronger stellar feedback, produced DMDG has less stellar mass and has more dispersed shape. Also, the number of star clusters is slightly less in the stronger stellar feedback run at the bottom. So you can say that stellar feedback affects the formation of DMDG and star clusters. And so here is the movie of fiducial run with solar metallicity and low metallicity run. So you can see that star formation rate is a lot lower and stellar mass of the DMDG is smaller. Actually, it is a fourth in the low metallicity run. So also less number of star clusters are created in the low metallicity run, as you can see here. So in future work, we'll consider these items to complement our limitation of this research. Dependence of star cluster formation and DMDG formation on initial metallicity needs to be investigated. Also, stellar feedback, like early feedback, radiation feedback, kinetic feedback is not fully included, and full physics of interstellar medium, like radiation transfer, chemical chain, photoionization by UV radiation is not fully implemented. So if we take account of this physics, observed metallicities of DMDG and star clusters will be explained better. And numerical resolution of 1.25 parsec and 400 solar mass only marginally resolves internal structure like half mass, half light radius and ellipticities of star clusters. So we need to improve spatial and mass resolution and resolve individual stars to describe the physics better. And estimation for probability of this kind of galaxy collision in cosmological simulation or some kind of cosmological context based on observation is needed. So here is the summary of our work. We firstly demonstrated that high velocity collision, about 300 kilometers per second, of gas-rich dwarf galaxies can induce simultaneous formation of dark matter deficient galaxies, DMDGs, with stellar mass of 10 to the 8 solar mass and massive population of star clusters, SCs, with stellar mass of 10 to the 5 to 10 to the 6.5 solar mass. So our results from idealized simulations are in accordance with the observed properties of NGC 1052 DF2 and its member global clusters and NGC 1052 DF4. Thank you for listening. If you have any further question or comments, please don't hesitate to contact me. Thank you.